Hi, welcome to this video. In this video we will talk about Boolean algebra. Boolean algebra, it's the algebra of logic 1s and 0. It has some postulates which are the definitions or the rules that this algebra can do. So the first postulate or the first rule, it's that the definition of Boolean algebra, what it is. And basically it has two rules. The first rule is that we have two types of elements, and basically you have a 0 or a 1. Those are the two elements. And also we have two types of operations. In these operations, it's the dot operation, which is equal to the AND operation, and we also have the cross operator, which is equal to the OR operation. The second postulate, it's about the existence of the elements 1 and 0. So basically we have two rules. The first rule says that if we have a variable and this variable it's ORed with a 0, then this is going to be equal to the same variable. It also has another rule that if we have the same variable but we AND it with a 1, then we're going to remain with the same variable. So here we're presenting the existence of elements 0s and 1 and how we can relate them with the OR and the AND operator. The third postulate is the commutativity of operations dot and cross. And with this, it means that we can change the order of the variables and this is not going to matter. So basically what it says is that if you have A or you have B, then it means that it doesn't matter. You can also have B or A and the result is actually the same. Also, if you have A dot B, and it can be, we can invert the order, it can be V plus A, and the result is going to be the same. This is what we call the commutation. We can change the order, and the order, it's not going to matter. Actually, I have a mistake here. It's actually V dot A. So we can actually erase that. So the next rule is the associativity. Associativity, it means that we can associate variables, and if we associate them, it's actually the same. So for example, we can have, and we can associate two variables. We can say, okay, I'm going to associate B or Z as one term. But we can also say that we can have A or B and these variables associated, then or Z, and both expressions are the same. The fifth rule is the distributivity. And this is a tricky one because basically what it says is that we can distribute the OR operation and the AND operation basically as you have seen as expanding. So for example, this is easy to understand in the AND operation. For example, if you have A dot and then you open parentheses and then you have V plus C, this is very easy for you to understand because you say, okay, I'm going to multiply or I'm going to make the AND operation of this variable with this variable, and I'm going to distribute this variable also to the C. So you know that this can be A dot V, I'm distributing the variable A, or A dot C. This is easy for you to understand because you have already worked with these types of expression. What is not so easy to see is that if you have an expression, for instance, this is what is going to be weird, it's that A, you're going to distribute this variable to the V, and also you're going to distribute this variable to the C by using this operator. If you have this type of expression, you can distribute A with the cross operator to the V variable, and then you're going to AND this with the A. Again, you're distributing variable A cross C. This also works on from the right side of the equation to the left side. So for example, you can have an expression like this, and you can factor. You can say, okay, I have the term A, and the term A, it's the same. So you can say, okay, I'm going to factor the variable A, and I'm going to factor it, and I'm going to say A, V, or Z. And finally, we have the sixth rule. The sixth rule is the existence of the complement. And basically what it says is that if we have a 0, we also have a 1. And the 1 is the complement or the inverse or the opposite of the 1. So what we're saying is that if you have, for example, an expression that is A plus A inverted, the A inverted, it's the opposite of the A. And since we are making an OR operation, that means if A is 0, for example, then it means that the A inverted is going to be 1. So what that means is that these types of expressions, one of both sides of the expression is going to be 1. So because of that, this whole expression is going to be 1. And of course, we have the dual. If you have this type of expression with the OR, you can also have this type of expression with the AND. If you have the same type of expression, but instead of the OR, you put the dot, A inverted, that means that one of both sides it's going to be 0. Because of that, this expression it's always going to be 0. These are the rules of the Boolean algebra, and with these rules we can generate some expressions that are similar to other expressions, and that's what we're going to see in this video. We're going to see how we can reduce or how we can minimize expressions to better represent an equation or a function. So in order to do that, besides postulates, which are the foundations of algebra, which are the ones that I just explained, there are several useful theorems. Think of theorems as shortcuts that help you minimize the expression even further. So there are around 10 theorems, because the theorems are no rules. So we're going to see 10 theorems of Boolean algebra. The first theorem is very simple. It's called idempotency. You can have something like, this would be something in regular algebra, it would be a to the power of 4. However, in Boolean algebra, this is not true. This expression is equal to just one a. It doesn't matter how many times you have the variable a, it's always going to be a. The next theorem is the neutral elements of the operators dot or cross. Anytime you have an OR operator, it doesn't matter what you have here or on the other side, as long as you have 1, 1, the whole expression is going to become 1. And the same applies for the AND operator. You can have 0 dot anything dot anything. It doesn't matter what you have on the left side or on the right side of the expression, as long as if you have an AND operation, if you have a 0 over there, then the whole expression is going to become 0. Another theorem is the involution. It's related to the inversion, to the existence of the inversion. So if you have any expression, it doesn't matter what type of expression you can have, and you invert this whole operation, and then you invert this again, then it's actually as if you hadn't done nothing. The fourth theorem is the absorption. We're going to be referring to the first expression as the A part of the theorem 4, and this is going to be the V part of theorem 4. So A part is the sum of products way of doing this expression, and the V is the product of sums way. And we refer to this as the dual. This is easy to understand. So when you have these types of expression, you can do something like this. So if you have this, you can use the factoring. So you can factor this, and you can say, okay, x, I'm going to factor it, and to get x, it's going to get 1, because x dot 1 is going to give you x, and or y. And of course, you know that 1 plus anything, which we have already seen, 1 plus anything, it's always going to give you 1. So this is equal to x dot 1. And we have already seen, because of the postulates, that we have the existence of the 1, and anytime you have x dot 1, this is going to give you x. So this is a way to prove this theorem. However, theorems, remember, exist in order for you to get shortcuts. So whenever you come up with this type of expression, you can simply say, I'm going to use theorem 4, I'm not going to do the whole procedure, and I'm going to assume that this is correct. So let me give you an example. You can say it's, okay, I'm going to use these both terms, and by using theorem 4, and I'm going to use the A part of the theorem 4, which is the sum of products way, I can say that since this is as if I had variable A, so I'm going to make like a change of variable. So I'm going to say A is equal to Wx. That means that we have something like A or A zeta. And if I have that, because of theorem 4, I know that the result is going to be equal to A. All this by using theorem 4, you say, okay, the whole expression is only Wx. However, the interesting thing here is that you can omit all this part. You don't have to write all this. I would recommend you that you do this in the first times you start working with Boolean algebra, because you're trying to understand that even if theorem says that you have variable A can be any expression as long as it repeats one side and on the other side of the expressions. Theorem 5, it's a different one. We have some expressions. Like for example, I have A or A inverted V, and this, what it says is this expression is going to be A or V. I'm not going to go with the whole explanation of why this is true. Remember, theorems are shortcuts, so what it means is that anytime you see an expression that looks like this, you're just going to get this result. And I'm going to give you an example. What happens if I have here we have a without inversion. Here you have a inverted. So I'm going to make a change of variable. I'm going to say, so that means that a inverted is equal to x inverted inverted. And this, of course, if we have 2 times the inversion, this is going to be equal to x. So if I rewrite this expression, we know that the result is going to be a or v because of theorem 5. And if we do the change of variable on the opposite way, so we're going to see that actually the result is going to be x inverted or v. Again, you don't have to do all this. You don't have to actually write this when you're doing this problem. You can say, okay, I'm going to use theorem 5. This is all I ask of you. I'm going to use theorem 5, part A of the theorem. The second part of the theorem, which is the v part, and it's the opposite. We can also do this with product of sum expression. Now let's see theorem 6. Theorem 6 is similar. However, you can see that the difference between theorem 5 and theorem 6 is that in both sides of the expression we have 2 variables. So in this case, I'm going to go with the dual part. I'm not going to explain the sum of products. I'm going to go with this one here. Let's assume you have some expression like. So what happens? Well, with this theorem, with theorem number 6, you can say, I'm going to use these expressions, these 2 expressions, and I'm going to use theorem 6b. And with this theorem, I notice that we have one variable, this variable here, and this variable here. This expression that has 6 variables, it's actually equal to w or c. As easy as that. Again, I'm not going to go with the explanation. This, you just have to look at patterns in functions. In this case, the pattern was to find one expression, in this case x inverted and x, that in one side of the expression it's normal or regular, and on the other side it's inverted. Let's see another example for theorem 6. So what happens if I want to reduce this expression? So here we can make a change of variable again. Remember, this is not necessary, but for the first exercises I might recommend you that you make a change of variable. So in this case, I'm going to make a change of variable, and I'm going to say w is going to be equal to xy. So I'm going to make this change of variable, and I'm going to say I'm going to rewrite this expression. So every time I find xy, I'm going to write w. So this expression is actually going to be. With this theorem, again, remember, you see one variable normal and we see another variable inverted. And with this expression, we say, okay, because of theorem number 6a, then this is going to become w. However, w is equal to xy. So of course, this is going to be xy. So the lesson here is don't expect to find expression exactly as shown on theorems. In this case, variable a, if you remember theorem 6a, Theorem 6a said a, v, or a inverted v. So don't expect to find a in this type of expression. I mean, well, in this case, actually, it was the v part. The v part, don't expect to find just one variable. In this case, the v part is xy. So you can have different types of expression as long as they repeat, or as long as you find the pattern, it's going to be correct. Now we have another example with theorem 6b. So in this case, you have to find something that looks similar in one side of the expression and on the other side of the expression. In this case, I have seen that a or c inverted is repeated here. So I can rewrite the expression as a or c inverted. I'm sorry, I made a mistake there. I'm going to write it below. So I can rewrite a or c inverted or v inverted. And then the second expression, I'm going to rewrite the other side. I'm going to put a or c inverted or v. So as you can see, this one here is repeating here. So basically, by using theorem 6b, you can say this expression, it's actually going to the inversion part is going to be removed, and we are only going to have what it's not inverted. So we're going to have a or c inverted. These two expressions are reduced to this expression, and then of course we are going to write the remaining part. Now here the lesson is, don't expect to find expressions next to each other. Also, don't feel the need to multiply or expand functions. As you saw, you can work also with the product of sums. This is one common mistake that you make, that you want to do all the expressions as you're most familiar with, which is the sum of products. So now for Theorem 7. Theorem 7, it's a little harder. As you can see, we have one variable, which is in this case we're saying it's v, and we also have v inverted on the other side. And when this happens, this one here, which is the inverted part, this one here disappears. And also we have the dual, so it's the same. Here we have this variable, which is the inversion, and this inversion is disappearing on the right side of the equation. We also have DeMorgan's theorem, and this is very important. One common misconception is that when you have something like, to think that this one here is as if it was variable x, and this one here is as if it was x inverted. And this is totally incorrect. Be very careful. This is not correct, because if you take this expression a or v inverted and you use DeMorgan's theorem, you can see that this expression is actually a inverted dot v inverted, which of course is different than this expression here. So be very careful. This is one common mistake that you make a lot, and hopefully you will get used to it. And of course we have the dual part. When you have a dot v inverted, you're gonna be the expression is gonna be a inverted or v inverted. Now we have the hardest theorem, which is Theorem 9, and basically what we say is that we have three expressions, and these three expressions, as you see, are going to be reduced to one. How do I see this expression? Well, it is actually not that difficult. You have one variable, you have variable a, and this variable it's repeated but inverted. Then you have variable b and variable c. You have two different types of values, and then these two values are together in the third expression. When you have this disappears. And the same happens with the dual. Again, you have a and a inverted, you have the v and the z, and these two variables that I have circled are together here. So because they are together, this one here disappears. Again, this is a shortcut. You can do the whole mathematics or the whole algebra of this, but you're always going to get to the result. And finally, the 10th theorem is the Shannon's development theorem. And basically what it says is that, well, this is the only theorem that its work, it's not to reduce expressions. Its work is actually to increase expressions, to make expressions larger. And we're going to see this with an example, because this is actually a very generic formula, so hopefully you'll understand this better with an example. So here's a summary of all the postulates and theorems. You can see here we have the postulates, which are the rules again, and here we have the theorems. And basically with these expressions, we can reduce any type of expression into hopefully a better and reduced Boolean logic expression.